Hi, everyone. So this is a bit uncomfortable. I stand between you and lunch, unfortunately. And I'm not going to make it any easier because this talk is going to contain a lot of references to food. But then again, I just hope that it will whet your appetite. And compared to the people on the other room, you will find lunch to be a little more delightful today. Over last year, we've heard a lot about direct style programming in Scala community. Martin Odersky in his Lean Scala article and in many conference talks, he's been speaking about Project Caprese and kind of giving it as a alternative to monadic style programming when it comes to effect handling. In Java, we got Project Loom released in Java 21, which was last year. Project Loom, if you guys don't know about it, gives native JVM way of running virtual threads. You could call them green threads, runtime threads, anything. But previously, Java had only OS level threads, which are like far more resource intensive. But virtual threads, you can have thousands of them running now in a single JVM. Combining these two forces, we now have some libraries, budding libraries in Scala. One is from Software Mill, Ox, and Gears from EPFL, which is combining these two elements and then giving direct style way of handling effects. So, question to ask, are we heading to a future with no monads? Has Project Loom thrown down a gauntlet on Fiber Party? Is it really all that better? But wait a minute, what is this direct style way of writing code anyway? We'll look at that and some of my observations on direct style way of handling effects compared to monadic style, which is popular in Cuts and Zio. I'm not going to do any performance comparisons for you guys because it's going to be very subjective. And we are going to look at Cat's effect for monadic style way of handling effects and Ox, which is from Software Mill for direct style. Food. So we're going to look at this recipe of Japanese dish, tonkatsu ramen. It's a ramen bowl, and it's got many components in it. And the first thing is the broth, which takes about 12 hours to cook. And then there is chashu, which is braised pork, which is cooked in an oven for about 3 hours at 180 degrees. And then there is obviously ramen, noodles, there is soft boiled eggs, and then there is veggies and mushrooms. So I've chosen this example because of the complexity involved in the recipe itself. It goes on for 12 hours, and then a lot of things can go wrong. And you are doing multiple things at the same time because broth is going to take 12 hours. What are you going to do? You can prepare your chashu at the same time. All of that. So we're going to look at some scenarios this recipe renders us when we take this and write code for it. So those scenarios we're going to look at is types, how to handle failures, concurrency, resource management, and testing. Let's start with types. No functional programming talk is complete without looking at types. And we're going to start with looking at Cat's effect. So I'm going to use Cat's effect logo, and then it's going to be down here so that if you zone out and then come back, what am I looking at? Look at the logo. That will say what library we are looking at. What I've done is I've taken all the components which you saw in that bowl, and then I've created the function signatures for them. Prepare broth, chashu, etc. And all of them take ingredients, and once you cook it, you get the actual thing out. And then they have been represented as broth data type, chashu, soft boiled eggs, blah, blah, blah. And then an interesting thing about Cat's effect is it allows us to represent the impure operation, which is the effectual operation, which is cooking the thing in this foundational data type called IO, which comes from Haskell. So the IO data type shows that there is something happening which is effectual, which involves communicating to the outside world. And then once that is done, whatever you get as a result of that computation is placed in one of the type parameters which is there in IO. There's just one of it. And a lot of things can go wrong. And there will be, well, if you cook something once and then you cook it again, you don't get the same taste. So there's the undeterministic nature of it. A lot of things are encapsulated in this IO type. And once you have these components ready, then you're actually assembling the ramen bowl, which will be all of the prepared components, which is broth, chashu, and all. You're trying to put the bowl together. And the putting the bowl together is obviously another real world action. We're going to wrap ramen bowl in IO and then give back. An interesting thing to note is that the parameters here are not actually IO data types, but the finished product. And we are passing all of them into the ramen bowl, and we get the ramen bowl out. Now, how do we put all of this together and execute? IO is a monad, and then to run sequential operations in IO, you would call flat map one after another. And Scala has a neat little syntax issuer for that called for comprehension, where you could sequence all of these one after another. And once you have all of that ready, then the last step here actually depends on all of the previous steps to have completed. And once that is all of broth, chashu, etc. are done, you have the assembled ramen bowl, which can look at all the previous operations and take out what the finished product was and then use it. And if things go wrong, the for comprehension allows us to, flat map allows us to exit as soon as there's an error, so that you're not at assemble ramen bowl stage without having all the components. So you never call assemble ramen bowl. And then once you have all of this done, we yield the bowl back, which means that now we have put together an IO of all the IOs together. So you have the massive big IO, which is IO of ramen bowl, which contains inside it a way to execute all of the smaller IOs, and then how it has to go through. So that's how Cat's effects IO works. There are some nice features of IO. First thing we are going to look at is the laziness of IO. Consider I'm looking at these two functions, cook ramen, soft boil eggs, and then you are making a pack of ramen for yourself, and a friend shows up at door, says they are hungry, and then you cook another pack for them, and then assemble it all together. Now, we've called cook ramen twice here, inside the for comprehension. But we can actually extract that out into a name, and then put the name in the for comprehension twice. This has the exact same behavior as the previous one. So that means that IO being lazy allows us to refactor things very easily without changing the behavior of the code, which is really important. These two things, one, clear-cut types representing the impure operations, and the laziness allows us to use IO in a very popular application architecture style in functional programming called imperative shell and functional core. So you have this functional core which will represent your domain logic, domain types. It's all pure functions which work on those data types, and you could write everything in pure functions there. And then we have this imperative shell which will interact with the outer world. It could be an HTTP API, it could be database connections, any of that. Once you get the data in from those outside ports, you pass it into your domain logic. And where it works in a deterministic style, you don't have any surprises. You can easily test it with mocks and all of that, and then give it back to the imperative shell to send it outside. So the types here and the laziness gives you this really clear-cut boundary between pure and impurity in your application. But there are some pitfalls. We're going to look at this pretty famous article, What Color is Your Function, by Bob Nystrom. It's pretty old. It's from 2015, but still holds really well. Consider this hypothetical language where for every function you write, the signature should be tagged with a color. So there are only two colors. One is blue, one is red. You always should tag your function with either red or blue. There's no other way. And there are some rules which govern how these functions are composed, called. To call the functions, you will have to always pass in the respective color at the end of the function call. Blue here for Azure, and carnelian gets red. And the way to compose is, you are allowed to call blue functions from within red functions, but you're not allowed to call red functions from within blue functions. If you want to call it, you will have to turn the blue function into a red function in the signature itself. Now, if the analogy is missed, here blue functions would mean your pure functions which don't have any effortful operation. Red functions would mean the ones which have IO computation, and IO is the red tag here. If you do this, if you like, let me turn my blue into red, what happens is your code is going to collapse and all of it will be just IO everywhere. All of your code base is going to be, all the functions going to be returning IOs. So that's one thing which needs to be careful about, that how do we make sure that our boundary stays and we stay sane. Now let's start with Ox. Ox does not have a logo at the moment. I've just used emoji inside the same hexagon. Hopefully they'll use hexagon. I don't know. With respect to Ox, this is probably the essence of direct style programming. It involves no monads to represent any impure operations. It's all data just right in the function signature. So we have broad, chashu, etc. Without determining whether there's pure function, impure function, we don't know. But it gives us a way to reduce the ceremony, I believe, is the right way to term it. It makes it a little more accessible for people who are coming in new to the functional programming world. And it allows us to do pretty simple things. And how do you compose all of them together? Just call their functions. And Ox, which we are seeing as the runtime, what happens is when you run this, it runs within a virtual thread. And every time there is like a operation which involves calling something else, in this case, preparing the broth, which will take some amount of time, the virtual thread is suspended and then taken off the context until the operation is complete. This is done via yield points in virtual threads execution. And once that is done, the thread is brought back into context and then the operation continues. It looks straightforward. And in a sense, direct style way of writing code would be something you would have learned in high school, like Python or anything in that sense. So that was with types. Now let's look at handling failures. We saw the whole overview of the recipe itself. We're going to focus for this section on tonkatsu broth. So tonkatsu broth is a stock which is made by using pork. And what it involves is taking a big pot, putting a bunch of pork meat into it and some other ingredients, bringing it to boil and simmering it to about 12 hours. This allows pork to get melt and the fat inside the pork to melt and then get combined really well into the broth. So a lot of things can go wrong. A lot of things can also go well. The broth itself, well, it needs to be monitored because 12 hours you can't leave it and go to a movie. And there are things which might be happening in the broth when it's simmering. And the things which could happen is there could be scum building up on the top because pork has a lot of fat. It creates scum just like soap, which needs to be taken out. And obviously, since it's boiling, it's always losing water. And that needs to be taken out. That needs to be added in. If you see that it's going down, or else your meat will just burn in the bottom. So I'm representing those as these functions, which are, well, IO, because we are doing the real world thing of like looking at it and stuff, looking at your pot. Scum level I've represented as an enum of low, medium, height. And think of like get scum level here to be like that impure operation where you are seeing how much scum has built up. If it is high, then that means that we have to take corrective action. And we have to signal somewhere that something is going wrong. So I've used this combinator in IO called raise error, which will turn the computation into an error condition once it resolves. If it is not high, then we are good. We'll just return the unit type there. Similarly for water level, If the level goes below 70, we are going to say that something is going wrong. We need to handle it, or else just unit. Similarly, we will also have to carefully monitor whether the broth is like boiling too much or it is boiling too little. In this scenario, I've used a little more denser information. I've used error ADT, high heat or a low heat variance on the error ADT. Checking temperature, if the temperature is little less than what you expect, you say that it's on a low heat error condition. If it is more than what you expect, you say that it's in a high heat error condition. So we have these all checks ready. We will write a procedure to monitor the broth itself. Now, what we're going to do is we're going to monitor scum, and I'm using this combinator handle error width on IO, which will allow us to go peer into what the error is and then take a corrective action on it. And with check scum, which means that we have to remove the scum. With my water level, which means that we need to add back the water. I'm just using println, but you get the gist. And with temperature, we now have we need to handle it with a nuance, because based on whether the heat is low on the broth or high, we'll have to take the right corrective action. So that's done by recover with, which gives us a way to see what the error is. So once you have all this, we have to get this going for like 12 hours. And probably you can just see, monitor it you can open the pot and see it once a hour, and that's on io.sleep. And then we had to do all of these one after the other. We see the scum, we see the water level, see the temperature, and then I've sequenced them through, this left shark operator, which means that it's going to disregard the left output and then hold on to the right output. And once we have that, we have a list of IOs. Then we can call sequence on it, which is from traversable. And what it'll do is it'll take this list of IOs and make it a giant IO of all the tiny IOs inside it. So that's our monitor broth. We'll look at the aux code for the same. Before we do that, we have to take a step back and look at some Java code here. And these are the rudiments of virtual thread in the JVM now, which is there is start virtual thread, which takes in a runnable. A runnable is a very pedestrian interface. It has no return type. It has no way to signal errors. It's just void run. So the only way to signal errors is through exceptions. And the way to return values out is through it's too much. Same stuff. And since instead of IO, we just have units. Oh, I have made a mistake. Ignore. And then when we hit the error condition, we are going to throw a runtime exception. And same with water level. And with check temperature, we're going to throw those respective subtypes of errors. How do we put it all together? We can call aux.sleep to sleeping the thread. This is exposed from down below the project loom gives like a sleep, which is exposed on aux level. And since they are all throwing exceptions, we'll have to kind of handle it with try, which gives us like failure and a success. And with respect to check temperature, you will have low heat or a high heat to handle. So that's with handling failures. Now let's look at concurrency story on all of these. So now we got this broth running, which is going to go for 12 hours. Now let's get started on chashu, which also takes 3 hours. Now if you wait for broth to complete and then start chashu, which is going to take 3 more hours. So why not start cooking chashu at 9-hour mark so that you have both of them ready to assemble the ramen bowl at 12-hour mark. So the chashu itself, you take a big slab of pork meat and then roll it into a roll, tie the strings on all the ends, and then you sear it a bit on the pan on all sides and then put it in the oven. The searing takes liquid, which is made of soy, mirin, and all of this, and then you take like in a casserole, you take it and put it in an oven for about 3 hours. for it to get slowly cooked and then absorb all the liquid. You will have to constantly monitor it in the oven. You will have to turn it around so it's getting evenly cooked. You'll have to see that whether it's getting burnt. And you will also have to see whether there's enough liquid left, or else you will end up with like a dry meat. So let's put that all together into code. Starting with chashu. Let's start with errors. What can go wrong? 4 things can go wrong. Your chashu could be getting burnt on one side. That means you will have to rotate it. There could be like too much liquid, which means that it is going to end up soggy. You have to remove the liquid. It could be getting unraveled from the strings. So you'll have to retie or add some more strings to tie it back together. Or it could be getting dry, which means we need to add more of that liquid. Similarly, we will have a function to do this check chashu, open up the oven, take out the casserole, see what's happening, and then raise relevant errors on if you see one of these things happening. And we're going to rate monitor chashu just like we wrote monitor broth, which is going to go for like 3 hours. And similarly, we're going to use handle error width on this and take respective corrections on all of these error types. And if nothing is going wrong, all the well, we're going to put back our casserole and close the oven. And probably we're going to monitor it once in 30 minutes. We open up the oven, pull out the casserole, check, put it back, take corrective action, put it back. And we're going to do the same charade here, which is like do toList.sequence.void. Now, we're going to put both prepare broth and prepare chashu together so that they both end at 12-hour mark. And we're still going to use flat map primitives on it. But we're going to use something interesting. We're going to call start on both of the IOs. So what start does is it gives us back a handle to the operation which is running. The handle is actually the handle to the fiber, which in CAT's effect runtime we would call as a runtime thread. And we're going to start the broth, get the handle to that fiber. We're going to sleep for 9 hours. And then we're going to get the chashu started, get the handle to that. And then you can call join on both of them. Join is the Unix primitive to wait for everything to complete kind of semantics. In this case, we are waiting for both of them to complete. And they both will complete at 12-hour mark. And at point we say that both chashu and broth are ready. Similarly, we'll look at aux code for this. We're going to rush through same error ADT for chashu, checking chashu. In any of the random instances, we will say that it's something wrong is happening. And the monitor chashu itself is going to follow the same structure as the monitor broth in aux. We're going to say we're going to sleep for 30 minutes and we're going to check the chashu and take corrective actions. And we're going to put it all together in aux. It's slightly nuanced. We're going to use a function called supervise, which takes a block of code, which means that I have to use braces in Scala 3. It takes a block of code and it bases its execution on structured concurrency. If you guys have not come across structured concurrency, it's a style of guaranteeing execution which solely depends on the structure of the code. In this case, the structure is the braces. It's the structure which is opening brace and closing brace, which is the thing, the scope. Anything which is running inside that scope is going to be guaranteed to complete by the time the program control reaches the end of the scope. In this case, we will have virtual threads running. And that is going, no matter what happens to any of the virtual threads, by the time the program reaches the end of the scope, all of the other threads are going to cancel. It gives us guarantees that we are not leaking resources. You could say that you are opening database connections within the scope, and then it's guaranteed that it's going to get closed. There's a lot of good stuff. we're going to use aux.fork, which which bases its work on starch virtual thread, which we saw earlier. But aux.fork here actually takes in a capability, which is provided by supervised. So the capability here is that it wraps all of the necessary requirements to start the virtual thread, that is passed from supervised into the fork. And the fork is not allowed to call from outside the supervised block at all. That's how aux has designed it around capabilities. So aux.fork, we're going to pass in again a block of code there. In this case, monitor broth. That means that it's going to get running immediately. And aux.sleep to sleep for 9 hours. And then while broth is still running, we're going to get the chashu going for the remainder of 3 hours and join on both of them. In this case, the join is on the virtual threads themselves. And I say that broth and chashu are ready at the end of it. Not everything can go right. You might not be paying attention, and then things might be on fire. We'll look at one such scenario and then see how cats and aux handle it. So I've added another case into this chashu error called catastrophic burning. That means your chashu is completely burnt in the oven and then it's creating fire. I added another case here, case 4, which means there's an even chance of everything to happen, unfortunately. That's not really the case, but then keeping it simple. In this case, the monetary chashu slightly looks different for this case. So all of the previous ones have just added print line, which means that they can be handled. But this burning thing is, can't handle. I'm going to just propagate the error back up. And in this routine, monitor chashu and broth prep, we'll have to kind of watch out for it, or else our broth is going to get stopped. So we're going to watch out for that to happen, the error which I propagated up. And then if it is that left here, that's by attempt, which is on the IO, which will turn any error conditions into either's to be handled safely, in the code. If it is left, which means that, chashu is gone, we are not going to terminate broth because broth is still happening. We don't have to throw out the broth because chashu is not ready. We are still going to join on the broth, and then at least we have a broth and you can cook ramen and eat without chashu. That's still a fairly decent ramen bowl. Similarly in aux, catastrophic burning, left of chashu error. And then here I'll use runtime exception because that's the only way to signal something really bad in virtual threads. That's because of this. There's no way to tell anything else other than throwing an exception in the runnable. And just use try on that because we need to safely handle that exception. And if you don't handle the exception, it's going to again cancel the broth preparation itself. So that's the way you would handle something really going bad. We're gonna next look at resource management. Anything which is scarce is a resource. And in cat's effect, now the resources we are using is basically oven and stove. And resource type in oven, so the resource type in cat's effect will allow us to safely pass in primitives which will allow us to acquire the resource and release the resource. And similarly for oven. The resource primitive allows us to do something like this. Inside the use, no matter what happens, it safely closes the resource. That means when you have the fire going in your oven, the first thing you have to do is turn off the oven. So that's what this is going to do. Similarly in aux, we're going to use this thing called aux.useinScope, which again depends on capability being passed by supervised, because we'll have to close the resource, structure concurrency. To two things it takes: a block of code to acquire the resource, a block of code to release the resource. And then you would use that later on, using scope, you would call on top of supervised and then add it. You will pass the system101 to that. Finally, testing. In CAT7 is pretty easy. Your test should not run for 12 hours because your IOs are 12 hours long. So they have mock time, which is exposed by async IO pick, which you can just write and run the whole thing in like milliseconds and use Scala assertions. But unfortunately in Aux, it is still an open thing where just because mock time is not available in virtual thread environments, it is not possible to mock time and write tests for this at the moment. And that's it. I have a small reckoner on what the CATS effect side looks and what the Aux slide looks. And if you guys want slides, it's here on the QR code. Thank you.